the fact that this is not going to work now.
Do you want me to join again or something? Is that a solution?
No, sir. I think it's an issue from our side.
I see.
There's a problem with YouTube. So
Okay, so let's start. No. Yes. Okay. A very good evening to all of you. HSS department is delighted to have Professor Arunava Sen to deliver the HSS departmental talk for 2022 Research and Industrial Conclave, IIT Guwahati. Professor Sen is a professor in ISI New Delhi. He is a recipient of number of prizes, 2012 Infosys Prize in Social Science Economics, Mahalanobis Memorial Medal of Econometric Society, Indian Econometric Society 2003, Koch University Prize for Best Paper in Economic Design in 1995. He is also a fellow of Econometric Society and was the past president of Society for Social Choice and Welfare. Professor Sen did his PhD from Princeton University under supervision of Professor Hugo Sonnenschein. His main area of interest are game theory, social choice theory, mechanism design, voting, and auction. The importance of his work has also been cited by Nobel Committee in 2007 when the Nobel Prize was given for mechanism design. His main contributions are in the area of implementation theory, where he has worked with with Bhaskar Datta, how can I? Yeah, and oh, okay, and in implementation theory, he has worked on subimperfect mass equilibrium, implementation of subimperfect mass equilibrium, and mechanism design. So he is also very popular among all the students in ISI. And now I welcome Professor Arunava Sen to deliver the talk titled Fostering Collaboration in Matching Platform. So, sir, you can start now.
Thank you very much, Amarjyoti, and thank you all for inviting me. It's a great pleasure to be able to participate. So I thought I would give you, I would tell you about some recent work of mine. Together with two Italian colleagues, Antonio Nicolo and Pietro Salmasso, who are at the University of Padova, and my former student Sonal Yadav, who is now a postdoc in Sweden, in Umeå in Sweden. So, I just, before I talk about the particular paper, I would just like to say, locate our paper in a more general class of problems which are of great interest not just to economists, but I would say to policymakers and even computer scientists and many other and several other disciplines. And this is the so-called problem of market design, right? And what is market design? Market design relates to allocation problems without money. Now, here you might say, well, this is not economics. In economics, you have markets, and then when demand is not equal to supply, then prices change, etc., etc. So why are we interested in allocation problems without money? I will actually give you numerous instances where allocations have to be made without money. For instance, to jump ahead a little bit, I'll say more about these things later, about how you admit students to IITs and allocate them across courses, how you arrange for, how you admit children to nursery schools, how you organize organ donations, where in almost all countries the use of money is strictly prohibited. It's illegal. So these are a very important class of problems. But let me begin with a description of the classical problem, which seems like a bit frivolous, a bit non-serious, but you will see that all of them, all the problems that I will talk about are outgrowths of this particular problem. And this is the so-called marriage problem of Gale and Shapley, written in the American Math Monthly of 1962. So what's the problem? There are M men and M women. Now you can, it need not be M men and M women. The cardinalities could be different, but let's just stick to this for the moment. Men and women have to be paired together or remain single. Yeah, so nobody is allowed to have multiple partners, but people can choose to remain single if they wish to. Now, each man has a ranking of all women as potential partners, and also over the option of remaining single. Similarly, each woman has a ranking of all men and the option of remaining single. Okay, and now the basic problem is how are men and women to be matched in some satisfactory way. And as you will see immediately, money plays no role here. All you have are rankings on both sides, if you will, of men over women and women over men. And the question is, do good matchings exist? So Gale and Shapley proposed this notion of stability. This is a criterion for a good matching. And when is a matching stable? So imagine, so we have a matching, some men are matched with some women, some remain single, and so on and so forth. So a matching can be blocked by if the following is true. Either a man or a woman prefers to be single than to be with their assigned partner. So you have a match, but the woman says, hey, I'd strictly prefer being single than to be paired with this man. And the other way that it can be blocked is that a man and a woman abandon their assigned partners in this matching and are better off by being together, right? Since there is no compulsion in matching. So if you force such couples to remain together, then that's clearly undesirable. It will generate all kinds of problems, right? So this is the notion of stability, right? This is the notion of stability. Here's another criterion which we may call incentive compatibility. So the question is, the natural situation to conceive of is that the ranking that every agent has over men over women and women over men are private information known only to the man or the woman concerned. So if the matching has to take place, it must be on the basis of declared preferences, right? People say, okay, this is my ranking, that's my ranking, and then there is a computer or a platform which brings these people together. And now if you do that, then there is the immediate specter or prospect of some people being better off by lying about their ranking, right? And the question is, is it possible to design, is it possible for the platform or the centralized computer to arrange for matchings in such a way that people do not have incentives to lie about their rankings? If they lie, then who knows, what's going to happen. Okay. So this is what Gale and Shapley proved in their famous paper of 1962, that stable matchings always exist, right? And this is by no means a trivial conclusion, because or even an expected conclusion, because this is actually quite a delicate result, and it fails if instead of two sides being matched, you want to match more than two sides, like three sides, or you have only one side, then all kinds of problems start appearing. Anyway, so here is
YouTube.
Hello, can you hear me?
Yes. Yes, sir. YouTube is live now.
Yes, sir. We can hear.
Yes.
Yeah.
Oh, okay. So YouTube is live now. There was some technical problem,
Okay.
so
So
now it is live.
okay, excellent. So the Gale-Shapley algorithm, Gale-Shapley proposed an algorithm which is called the deferred acceptance algorithm. And here is the a description of the algorithm. This is one possible algorithm. As you can see that there are other algorithms possible. So this is what's called the men proposing algorithm. So all men propose to their highest ranked partners, right? So everybody proposes to the woman they like best. And this may result in some women not receiving any proposal or some women receiving multiple proposals. So women who receive multiple proposals look at their ranking of men and select their most preferred man amongst the people who propose to them, and let the others go, reject them. And what happens is that in in the next stage, all the rejected men propose to uh, their second highest partner. So they cannot propose to somebody who has already rejected them. Then they propose to their to the best available partner, and women again receive proposals, and they select the best among them. And here they may select amongst those that including the person that they have left over, okay, from an earlier round. So there may be one particular woman, say woman W1, who had received 5 proposals. She had kept one, and now in the second round another 3 proposals are made to her. Then in this 3+1 she will select the best and again let the rest go. So then the rejected men again propose to the best among partners who haven't rejected them, and so on and so forth. And it's easy to see that this process will converge and will lead to a stable matching, right? So there will be nobody who will there is no man-woman pair who will wish to block this particular the allocation or the assignment generated by this algorithm. It's quite easy to see that. And you can also show that no incentive compatible matching mechanism exists. It's not possible to have something which is stable and incentive compatible. I'm sorry, this statement that I've made is not absolutely correct. I mean, there is no incentive compatible stable matching. Okay. So I can always have an incentive compatible matching by just having a fixed matching. It does not depend on anybody's preferences. That is going to be incentive compatible because there is no point in lying. Nothing will change. Okay, but no incentive compatible stable mechanism, stable matching mechanism exists. Okay, so let me say a few words about applications. There are an absolute plethora of sub applications. Very popular one is school choice. And what is the aspect of school choice which is different from that of the man-woman model that I had discussed earlier? The thing is that the school can admit more than one agent, right? Can admit more than one student. And now this is really an incredibly active area of research. Let me say, for instance, that there is a paper written by 2 Turkish guys about admission to IITs in one of the most prestigious journals in economics, the American Economic Review, in 2017. And basically, they are interested in questions about how to adapt deferred acceptance to things like affirmative action, quotas, reservations, and so on and so forth. So this is a particularly interesting theoretical problem, right? And there are many papers being written on such things. The other application, or another application, is the organ donor exchange problem. So there is a famous paper by Roth, Sonmez, Utku Unvar called Kidney Exchange in 2004. And the idea is that how should kidneys be allocated amongst various recipients. So the point is that every um, think of a person as being as requiring a kidney as well as willing to donate a kidney. It's not the same person, but for every person who wishes or needs a kidney transplant, typically has to arrange for a person who is willing to donate a kidney. Now, the problem is that kidneys are not all compatible, and your kidney donor's kidney may not be compatible with your own requirements, but it may be compatible with somebody else's requirement whose kidney may be compatible with yours, and so on. So the whole paper is about how to arrange these large cycles so that you can improve the efficiency of of the whole transplantation process. Let me just mention that the Nobel Prize in Economics in 2012 was awarded to Shapley and Roth for their work on market design. It would definitely have been also awarded to David Gale, but sadly he had died by 2012. Shapley was alive, and he did receive it. And let me just say that this is an incredibly active area for research, and I hope my sort of brief description of examples convinces you that there is a lot of scope for analysis of this kind. So what do we do? So what is our paper about? Our paper has this additional feature that we are matching agents together in order to work on a project or to perform a task, right? So you're not just matching people together, you're matching them with an object or a task. And there are two important features of this model which make it somewhat different from the models that I have just described. That in this case, agents are not divided into two sides like men, women, firms, workers, etc. So this is part of a genre called roommate problems, right? So they're roommate problems because gender isn't particularly important. And the other thing is that agents have preferences over objects, but objects clearly don't have preferences over agents. So it's not a simple three-sided matching problem where there are three categories of people. So this is kind of like a 2.5 category, if you will. So here are some examples. So, collaboration amongst research groups on scientific projects, right? So, there are typically calls, funding calls from various groups of people to work on scientific projects. So you can, your department, the IIT Guwahati Economics Department or Humanities Department can propose a project on something with some other department, with the Indian Institute of Science, Bangalore, some department on something, right? So you have so there are multiple such proposals, and the job of the central organization is to decide which proposals to fund. Okay, that's the question that we're interested in. And so, for instance, a firm has several tasks that need to be performed by teams, and how should they be assigned is a question. And a more personal, or certainly, what motivated me to think about this was, we often assign, we have thesis or projects to be assigned to students, and very often we like to assign them to more than one student because they work well in collaboration with each other and so on. So we are looking at a specific case of exactly two agents who have to be matched with one project, right? So you might ask, why not something more general? The general problem is actually, there are some technical difficulties, and really the for the needs of shall we say clarity, the two agents and one project is really, we think of it as the leading case. Okay, so what do? We show that in an environment with some restrictions, we propose an algorithm, um, and this we call object constrained maximal matching algorithm, OCMMA. And what it does is that it achieves stability. It also achieves Pareto efficiency. And finally, it also achieves incentive compatibility. So this comes with the cost that we restrict preferences, as we shall see. Okay. Okay. So what do we have here? So let me outline a model very briefly. So there is a set of n agents, n equal to blah 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 I j, and a finite set of objects a b c, etc., etc. And agents either remain assigned or paired with another unique agent. So a single agent is not allowed to have multiple projects with multiple partners. I mean, you might say that the funding agency has constraints and does not want to assign the hundreds of projects to the same agent, and once they remain assigned or paired with another uh, unique agent, they can be assigned with a unique task or an object, right? And of course some okay, so here I've made an important typo. Either remain unassigned, right? So either they can remain unassigned or they are paired with another unique agent and a unique task object, right? They can remain unassigned as well. So you're by yourself. You don't get anything, right? All your proposals are rejected. And we assume that there are many objects, at least as great as half the number of agents. So if you're applying for scientific projects, there are no shortage of scientific projects that you can propose. I mean, um, there is no limitation on that. And an assignment alpha is a collection of triples ija, where object A is assigned to the pair ij. And we also have a distinguished object called A star, which is, you don't get any project. It's the project, no project. And I empty set A star denotes the fact that I is not assigned, right? Or is assigned this dummy project A star. So here is an example. So there are, let's say, 1, 2, 3, 4, 5, 6 agents. There are objects A, B, C, D, objects, tasks A, B, C, D, and an assignment could be something like 1, 2 get A, 3, 4 get B, and 5, 6 get C. And another one could be 1, 4 get A, 3, 5 get B, and 2 and 6 remain unassigned, right? They're on the, they get nothing. Okay, so our preferences can be very nicely captured by a graph. So this is the example that we were talking about. So there are 6 agents. They are represented by nodes of a particular undirected graph. And agents are nodes. And if 2 agents are linked, these agents are compatible. Okay. And so note that there is an element of mutuality here. It means that one wants to work with 2, and that also means that 2 wants to work with 1. It's not the case that 1 wants to work with 2 and 2 does not wish to work with 1. This is an important feature that of our model. So it's not the case that that we want to work with Harvard, but Harvard has no interest in working with us. So so notice that certain agents are not linked or don't have an edge. Like 1 and 5 are not linked. 6 has no links with anybody. Neither are 2 and 4 or 3 and 5 linked. Okay. Those agents that are linked, typically, we may have some objects which are which are described on the link between those two agents. So there is, so CD in the link 1 and 2 mean that C and D are projects that are first choice projects for 1 and 2. And a project which does not appear there, for instance, F does not appear on the edge between 1 and 2, it means that 1 and 2 are, they could work together, but they don't really like F. I mean, F is not their specialty. So 1 and 2 have many close collaborators, but F is a project which really doesn't fit in well with the interests of 1 and 2. Okay, so edges are labeled by objects, and they're these are their so-called first choice projects, and actually we allow them to be empty, right? So they don't have any good projects to work on, but they could collaborate in general. And the set of and again, an important thing is the notion of mutuality. The set of first choice projects that I has with J is not necessarily the same as I's first choice projects with K. So IIT Guwahati may have some projects it might wish to execute with IIT Kanpur, but not perhaps a different set of projects with IIT Delhi or something like that. Okay. And so preferences have a very simple structure here. So for every agent, we have a bunch of triples involving that agent, which are, the highest of those preferences are those when an agent I is assigned a project with an agent J with whom she has an edge, and they are performing a first choice project. A second, below that is if I is paired with J with whom she has an edge, but is not assigned a first choice project. And this we shall call a remainder project. And the third is to remain alone, right? The third is remain alone. And the worst is if you are paired with an agent with whom you don't have any edge, with whom you are not a collaborator, with whom you don't wish to collaborate at all. Okay, so you have 4 layers of preferences or 4 indifference classes. Okay, so let me give you an example. This will make it clear. So let's look at the preferences of agent 1. So for the preferences of agent 1, 1, 2, and C is the best, right? Is the best possible. Now notice 1, 2, and C, and 1, 2, and D, 1 is indifferent between, because they both involve working with an agent whom she likes to work with, and on a project that they have that is a common first choice object. So 1, 2, C. Now look at 1 and 4. And B. So 1 and 4 are connected, but B is not something which is a first choice, which is a remainder project. So 1, 2, C is strictly preferred by 1, 2, 1, 4, B. And then in the third, this thing is 1 and A star, 1, not getting anything. And the worst of all is if 1 and 5 were paired together. 1 and 5 don't have a link, but they are paired together and told, okay, you perform A. Now that they would hate. Now look at 6, for instance. 6 is completely by herself. So 6 would prefer to remain by herself than to be forcibly inducted with 4, for instance, to perform B. And the question is, given our setup, how should a centralized agency and platform, perform this assignment? What's a good way to allocate amongst these agents? How is a good way to put these guys together and give them projects? Okay, so again, what we need to do is we'll talk about the core. So consider the allocation or stability. This is strongly related to the notion of stability. So let's have 1, 2, B being matched with 3, 4, C and 5, 6, D. Now this you can see is kind of a stupid way to do things, because For instance, look at 1, 2, 3, and 4. Look at the coalition or the subset of agents 1, 2, 3, and 4. Now, what 1, 2 can do is that they could 1, 2, and 3, 4 could swap projects. 1, 2 could now perform C, and 3, 4 could perform B, and then 1 and 2 would move from their second to their top indifference class, as would 3 and 4. Likewise, 5 and 6, as far as 6 is concerned, or 5 is concerned, 5 can just block as well and say, look, I prefer to be on my own. So I'm in my worst class. So I would rather be, together with, by myself than be paired with 6. So a coalition can block if there exists an assignment pertaining to the coalition using objects available to that coalition that can make all members strictly better off. So what do I mean objects available to the coalition? Now look at the coalition 1, 2, 3, 4, right? So B and C are things that they already have amongst themselves, right? So they can just swap things amongst themselves. Now you don't want them to go and grab a project which somebody else has and say, okay, we want this. Because that wouldn't seem to be fair, right? If in an assignment somebody has been given a first choice project, then it doesn't it's unreasonable to assume that their project can be snatched away by some other group and say, okay, we want this. Okay, so that's what we mean by saying that they have to use objects available to the coalition. Now our definition is a little more general. We allow for more blocking. We allow for blocking with the remainder objects of other agents who are paired together, but let's not go into that. So an assignment is in the core if it cannot be blocked. Okay, so what do we want? We want an algorithm to generate assignments that are not blocked in any what we shall call a preference profile, or a preference profile in this case you should just think of as the graph, right, as a labeled graph. Okay, what is Pareto efficiency? Pareto efficiency is a standard concept that all economists use. In fact, it's the only notion of efficiency. It just says that, look, all the agents cannot get together and sort of reassign themselves in some way such that nobody is worse off and at least one person is better off. So now look at this situation where, look at this particular situation where 1 and 2 are friends and like AB, 1 and 3 are potential collaborators like AB, and so on 2 and 4. But suppose you have the assignment 1 and 2 who get A, and 3 and 4 are left out in the code. Now notice that, this is again a rather stupid way of doing things, because what you can do is that you can put 1 and 3 together and 2 and 4 together. Give A to 1 and 3, give to B to 2 and 4, and then everybody is getting an object that they like. So everybody has moved. 1 and 2 have not improved, but 3 and 4 have improved from their third to their first indifference class. Okay. Now this is efficiency. You might say, well, how do I know that stability doesn't already cover this? And the point is that it isn't covered by stability because it is stable. Why? Because notice that 1 and 2 are in their first indifference class, so they cannot be induced to join any blocking coalition. 3 and 4 would like to induce them and say, hey, come and join us, but 1 and 2 are already in their first indifference class, so they will not join. So in fact, it is stable, but it is not efficient. So these two things are different from each other. Okay, so let me just mention incentive compatibility. So both the core and Pareto efficiency are properties that relate to a particular preference profile, or that is, they related to a particular graph. Okay. Now, incentive compatibility relates to the map that associates an assignment with every preference profile, right? Because then you can cheat, you can declare some other preferences, and then you'll get a different graph. And this map is called a social choice function. And again, suppose preferences are private information that they're required, they are reported to the platform, which uses the SCF to determine an assignment. So you report something and the platform then computes the assignment. Now, the first, then you realize immediately that agents can lie. For instance, I and J are linked, but they could report that A is not an FC project. It's not a first choice project when it is an FC project. So they could do things like they could cheat on the number on the projects which they actually like, and pretend that they don't like it, or they can pretend to like things that they don't like. They can also pretend that they are not linked to each other. Maybe that will help. And we say that a social choice function is group strategy proof if no coalition of agents can lie about their preferences and all be better off, right? So lying does not help by any group of people. Lying cannot improve all their, cannot, improve their welfare. Okay. And what we'll do is that maybe I'll just jump ahead to the theorem. So we have an algorithm which we called OCMMA, and that generates assignments that are in the core and are Pareto efficient, right? And the SCF generated by OCMMA satisfies group strategy proofness. So it's in the core and it is Pareto efficiency. And moreover, the SCF that it generates, the output that it generates at every graph, that defines a social choice function, and that is group strategy proof. And interestingly, a converse is also true. Suppose we have an arbitrary SCF that generates assignments that are in the core, are Pareto efficient, and satisfies an incentive property, which I don't have time to elaborate on, but it's something called Maskin monotonicity, and a technical addition. Now, suppose I take an arbitrary SCF which satisfies all these desirable properties, then we show that that SCF must be generated by an algorithm, by a suitable choice of parameters for the algorithm, right? So this algorithm is in some sense captures all possibilities. You can't really do much more than this. Okay, so to conclude, and I think I've almost run out of time, to conclude, let me just say a few words about this algorithm. So it's quite a simple sequential type algorithm, and it uses a 3-step protocol. So what it consists of are what are called choice functions, right? And there is a stage 1 choice function, a stage 2 choice function, and the remainder agents which are not matched by these choice functions are left unmatched. What is the stage 1 choice function? What it does is that, what does a choice function do? A choice function, takes as an input these partial assignments that place all individuals in their first category. Okay, so it could be 1, 2A and 3, 4B. That's a partial assignment where 1, 2 and 1, 2A and 3, 4B puts everybody in the first category. Okay, so that's one possible partial assignment. Another one could be 1, 3 X and 2, 4 Y or something like that. That's another thing. Then there are all kinds of other ways in which you can assign them together, in which you can you can have possible partial assignments, which put all the agents in their best category. Then this choice function takes that as an input, and what does it produce as an output? One possible assignment, right? So you look at all possible partial assignments which put people in their first category. There are several of them. So the choice function takes that as an input. And what does an output? It outputs a particular assignment. Now, this choice function has two properties. One is that it's maximal, right? So if it picks 1, 2A and 3, 4B, it should not be the case that it is also possible to have 5, 6X where 5, 6x also puts both 5 and 6 in the first category of preferences. So it must be the case that it is maximal, right? So it does not leave out the possibility that some agents are, that it is possible to still have some more agents put in their first category. And the second thing is a so-called contraction consistency, that if we have two possible inputs into this choice function, where the input in one case is a subset of the input in the other case, no, sorry. If from a large set, if from a particular set of inputs, you select one particular output, and then that same output is available in a subset of the original problem, then you should continue to choose this. In choice theory, this is what Amartya Sen called condition alpha, or contraction consistency, and this is actually very important for the incentive property. So when you're choosing these partial assignments, you should choose them in a way that is contraction consistent. Okay, so this is your first choice. And in the second choice, what you do is that you again do something similar, but the choice function in the second stage could depend on how you've chosen in the first stage. So again, you have a whole bunch of possible partial assignments. Now these guys are, you give them something which puts them in the second indifference class. And again, you satisfy some maximality and contraction consistency property with your second stage choice function. And then finally, in your third stage, anybody who is unassigned is, who is not assigned in either step 1 and step 2, is just told you stay on your own. So what OCMMA is a very simple sequential procedure, right? But the procedure has to have some obey certain consistency and maximality properties at every stage, right? And as we said, this is kind of the only way to satisfy good properties. So that's the sort of claim that we are trying to make. Okay, so I think that I've more or less said everything I wanted to say. I think I've probably run out of time, but if there's anybody who has questions, I'm very happy to try and address them.
Okay, thank you, sir. So please, either you can raise your hand or you can write the question in the chat box, if anyone has any question. Yeah, you can ask, I think. Debursida, you can ask.
Okay, thank you, Professor Sen. That was quite enlightening for the uninitiated like ours. So I just have two queries. One is the preference that you have considered. Does it appears to me that there is only indifference between, let us say, 1 and 2. Between 1 and 2, if they have like a compatibility with each other,
yeah,
then the two projects that you have mentioned, A and D, let us suppose,
yeah,
so they are indifferent between A and D, or
yeah,
let us say in this case A and B.
yeah.
But did you consider case that there is mutuality between 1 and 2, but they have preference also over, let's say, they prefer
Strict
C over
preference.
D?
Okay.
Yeah.
Okay, that's a good question. And in fact, we have chosen a very simple set of, a very simple description of preferences. They're called dichotomous preferences. You like or you don't like. The problem is, as soon as you have these strict preferences, right? Multiple strict preferences, right? I mean, one could have, in general, what are preferences for every agent? Every agent should have preferences over a partner and a project, right? Over this pair, right? So one could have preferences over 2A, 1 2A, 1 2B, 1 4F, 1 3E, etc., etc. And they could, for instance, all be strict. The thing is that you immediately have non-existence, right? So there's no way that you can actually hope to show that that you have existence, right? That's the problem. We believe, I mean, I don't want to motivate our choice of model by saying that this is a good model because it leads to some results, but we believe that this is kind of um, dichotomous preferences are a good description of reality, right? You like or you don't like, you know or you don't know. In referenda you say yes or you say no. And this particular class of preferences, it's a little richer than that, because you, there's an interplay between preferences over agents and projects. So you have multiple indifference classes, right? But it's true that this model, if you insist on a finer description of preferences, then various things then you get impossibility essentially quite quickly. Yeah.
Yeah, thank you. Just one small quick clarification regarding the theorem. So this OCMMA algorithm that you have,
Yeah. Yeah.
you're saying that it's going to generate core, it's going to ensure Pareto optimality,
Yeah.
but is incentive compatibility is ensured?
Yes. Yeah, I just wanted to make sure. I just wanted to clarify that, again, as I said, the core and Pareto efficiency relate to a particular graph, right? Whereas group strategy proofness relates to this social choice function map. What happens as you change the graph, right? As I change the graph, I get a different assignment. So maybe 1 and 2 can say, look, we actually like A, but we now say that we don't like A. Maybe we'll get something better, right? So it does satisfy group strategy proofness, but the object that satisfies group strategy proofness is the social choice function, right? So I mean, perhaps it's a little confusingly written, but what we are concerned with is the social choice function that OCMMA generates, and it generates that social choice function satisfies group strategy proofness and Pareto optimality and the core, by which we mean that at every preference profile, the allocation belongs to the core and is Pareto efficient.
Okay, thank you.
Thank you.
So, sir, I have one question.
Yeah.
So since it is means if I like agent, one agent, the other agent also likes me to do a particular project.
Yeah.
So if in this algorithm, if we assign all the first prep means the pairs whose project is the best one or the preferred one. So is it?
But there are multiple choices for this, right? There are multiple choices for this. It's not at all clear that you can see, for instance, here, this example. Okay, what is to stop you from choosing 1 2A and leaving 3 4 unassigned?
Yes.
Right? That's not going to be efficient.
Efficient, yeah.
Right? So because there are multiple possibilities. There are multiple possibilities.
And okay. And the objective of the social planner is to satisfy these three conditions.
Well, I mean, I've cheated a little. There are actually 4 conditions, because there's some technical condition as well. But the OCMMA is the only one which satisfies all 4.
Okay.
Right. So the 4th one is a technical condition, like some people who were not getting anything that they liked, now they no longer like each other, then it should not interfere with the choices of agents who actually got something they liked. Those kinds of, it's that kind of axiom.
Mm. But so this gives that there means actually, sir, if we have a connected graph, then
Yeah.
we will always have this kind of. But if there
No,
is
no, even if it's not connected,
connected,
that would be very easy.
okay, this.
Yeah, suppose nobody is connected, then everybody is on his own.
Yeah,
That's
yeah.
unique.
So that is. Mhm.
Yeah. But actually, if you have a very highly connected graph, it might actually
Very
be a
big
problem.
creates problem. Yes.
But you can, I mean, there is no problem ultimately, but, but you can solve that problem.
So any other question? Okay, so if there is no other question, then I thank Professor Sen for giving such a wonderful talk, and it was very it's enlightening for us also, in the sense that we came to know in a very simple terms the matching problem. So thank you.
Thank you. Great pleasure. Thank you. Thank you.
Yes.
Thank you, sir.
Thank you. So I'll leave.
Yes.
Yes, we will end the meeting now.
Thanks.
Sir, can I stop the YouTube live?
Yes, yes, of course.
Yes, now you stop.
Yeah, stop the live stream. Amar, should I end the meeting?
Yeah, yeah.
Okay. Thank you. Thanks, everyone.
Thank you.